Hello, my name is Mustafa Alperen and this is Lab 4 for Physics 2211, Oscillations. A quick overview of what I'll be covering in this slideshow is I'll go over an introduction of the experiment. I'll talk about the models, assumption, initial conditions, the systems, and the surroundings for our experiment. I'll talk about code I wrote for the initial conditions as well as the remaining of the lab. Then I'll compare the different graphs we get in our results and answer the questions of what does it mean. So the purpose of this lab is to examine the purpose of a spring mass system in which the mass swings in an arc while oscillating on the spring. Some fundamental physics principles used in this lab is the energy principle, which is the transfer of energy between different systems, which can be expressed as delta K plus delta U plus delta E thermal plus delta E other, whatever energies there are, is equal to work. And the Newton's second law, the force acting on an object is its mass times its acceleration. The force is also equal to the change in momentum over change in time, which is F equals ma and F equals dt over dmv over dt, which is also dp over dt. And so a quick preview of our main results is that the law of conservation of energy is proven because both graphs are very similar, and the energy total is always zero because a constant zero. The models we used was a time in seconds versus the x distance in meters, a time in seconds versus a y distance in meters graphs, and some assumptions we used was that the object has no other forces acting on it, such as other than like air resistance, other than what we're modeling for. Some initial conditions was that the mass is 0.402 kilograms, the position is negative 0.097 in the x, negative 0.632 in the y, and 0 in the z, and that there's zero velocity. The system is the mass spring and the ham dropping the mass, and the surroundings is Earth or just gravity. And on the left side, you can see our tracker video that I used over there. So the code for our initial conditions. So the mass of the ball, position of the ball, and the velocity of the ball is all given to us from either the video or the tracker data. So we just straight up input that into the code, and we calculated Ks and L0 from the code. We got T from just looking at distance of the 2 points to find the period. Calculated Ks to be m over T over 2 pi squared on the denominator, and then got L0 to be L minus mg over k, and calculated all of that from the previous data we again found from tracker. The remaining code in the glow script, we just used a different position update formula, such as ball velocity update formula, ball position update formula, and did energy principle, for example, k equals 1/2 m v squared, and then ug is equal to mgh, and then added all those together for Fnet, for example, over there. Fnet's equal to F gravity plus F spring, like just adding all of them together, and it's basically fulfilling the energy principle. So this is our observed versus models graphs. The red one is the actual experiment and the data we modeled in Tracker, and the blue one is the model that I built through GlowScript. And you can see that they're actually really very close. There are slight differences between them, but they're very close. Some possible errors, and this could have been that rounding errors in the calculation phase for calculating for K or T or L0 could have resulted in a different sort of model than what the experiment gave. The tracker video could have been plotted probably better since it was manual plotting, and that could have led to some more errors. There could also be more forces coming from the surroundings than what our model accounts for. Again, that extra surrounding force. So what does this mean? Is the energy principle satisfied? It is satisfied because E is always at zero. So if you look at the right-hand side, that graph, the E would be the orange line that's always going through zero. So it is always at zero, therefore it is satisfied. Comparison of the X period and the Y period. From the graphs in Tracker, we can approximate the X period to be 1.57 and the Y period to be 1.52. This shows that the X period is slightly bigger than the Y period, but they're still both very, very close to each other. And yeah, I just want to thank you for watching.